For this screencast for chapter 19, I have chosen a problem from the book, and the problem is that there are two flashlight batteries which are connected by nichrome wire of different length. Here you can see this is the thick nichrome wire and this is the thin nichrome wire. And problem number A says that if the EMF of these batteries are 1.5 volt each, then it says to find the steady state inside each nichrome wire. So what we are given is the length of thin nichrome wire is 0.5 meter, and length of thick nichrome wire is L2 equals 0.15 meter, and the diameter of thin wire D1 is 0.25 millimeter, and diameter of thick wire D2 is 0.35 millimeter. So now, before heading to the problem, let me get some equation. We know that the current in wire depends on cross-sectional area and average drift speed. So current in the metal wire can be expressed as I equals NAV, and we know that the average drift speed of the mobile electron is proportional to the magnitude of electric field. So V equals UE, where U is the proportionality constant called electron mobility. So now from 1 and 2, substituting I equals NAUE. So again, coming back to the area of thin wire is pi d1 by 2 whole square, which comes out to be this much, and similarly doing for thick wire, it comes out to be this much meter square. You need to be very careful about the units over here. And since these batteries are connected in series, the total EMF of the circuit is E equals 3 volt. And using the node rule from Kirchhoff law in steady state, which says that current in thick and thin wire must be equal, so I1 equals I2. Now this is the equation that we got earlier, and AUE, and putting this value, we come E2 equals A1 by A2 E1. And again, the using loop rule, it says that total difference, potential difference is 0, and so for this figure, the total EMF minus E1 L1 minus E2 L2 is equal to 0. So now putting total EMF in one side and other component in another side, we get this equation. Now substituting E2 from previous equation, we get E1 equals 3V and this component. Now putting this value, E1 comes out to be 5.2 volt per meter, and here also you need to be careful about the units. Now similarly substituting E1 in equation 4, we get the value of E2 to be 2.65 volt per meter. Similarly for equation for problem B, it says us to show the electron takes around 36 minutes to drift through this from location B to A. So as we said earlier, average drift speed of electron in thin wire is V1 is equal to E1. As we know, V1 comes out to be 3.6 into 10 to the power minus 4 meter per second. Similarly for drift speed of electron in thick wire, it comes out to be 1.9 into 10 to the power minus 4 meter per second. So since the electron takes to the nichrome wire from B to A can be given by T equals L1 by V1, that is distance taken by the velocity, and adding these values for the thick wire and the thin wire, it comes out to be 36 meters, and it proves the problem. Similarly for for problem number C, it says how many electrons cross the junction between the two wires every second. So I1 equals and A1 V1, and these are the values that we got earlier, and N1 is given as 9 into 10 to the power 8 more electrons per cubic meter, and substituting those values, it comes out to be 1.6 into 10 to the power 18 electron per second. And since the current is same in both wires, that is I1 equals to I2, it is same for the thick and thin wire, and since they are in steady state. Thanks.